Welcome to Sleepy Science, a place where curiosity slows down and the universe gently unfolds before sleep. If you enjoy calm explorations of mysterious ideas like this one, consider liking the video, subscribing to the channel, and writing in the comments where in the world you are watching from tonight. Somewhere out there, under the same sky, another listener might be drifting to sleep while thinking about the same stars. For a very long time, humans believed the universe was still and unchanging. The stars appeared fixed in place like small glowing points on a giant dark dome. Night after night, they returned to nearly the same positions, creating the quiet illusion that the cosmos was something stable and unmoving, something permanent. Ancient civilizations imagined crystal spheres carrying the stars across the sky, and for centuries this peaceful idea remained largely unquestioned. But in the early 20th century, something subtle began to reveal itself. Astronomers with increasingly powerful telescopes started studying distant galaxies, enormous islands of stars located unimaginably far away from our own galaxy. And when they examined the faint light arriving from these galaxies, they noticed something unusual. The light seemed slightly stretched, slightly shifted toward the red end of the light spectrum, a phenomenon that would become known as redshift. To understand this strange effect, imagine the sound of an ambulance passing by on a quiet street late at night. When it approaches, the pitch of the siren sounds higher, and when it moves away, the pitch slowly drops and stretches into a lower tone. This happens because the waves of sound are being stretched as the source moves away from you. Light behaves in a similar way. When a galaxy moves away, its light waves stretch slightly, shifting toward red. When astronomers measured this carefully, they began to see a remarkable pattern. Distant galaxies were not randomly moving around in space. Most of them were slowly drifting away from us. And even more surprising, the farther away a galaxy was, the faster it seemed to be moving away. It was as if the entire universe itself was gently expanding in every direction at once. This discovery was first clearly described by the astronomer Edwin Hubble in the 1920s. Using careful observations from telescopes placed high above city lights, he measured the distances to galaxies and compared them with the redshift in their light. The result was astonishingly consistent. Galaxies twice as far away were moving away roughly twice as fast. Galaxies 10 times farther were receding even faster. The universe seemed to follow a quiet cosmic rule. But here's where the idea becomes even more interesting. Galaxies are not simply flying through empty space like sparks from a fire. Something deeper appears to be happening. Space itself is expanding. The distances between galaxies are slowly stretching over time. An analogy that scientists often use is a loaf of raisin bread slowly rising in an oven. As the dough expands, every raisin moves away from every other raisin, not because the raisins are moving through the dough, but because the dough itself is stretching. If you were sitting on one of those raisins, you would see all the others drifting away in every direction. And no matter which raisin you chose, the same thing would appear to happen. Every raisin would feel like it was at the center of the expansion. The universe behaves in a strangely similar way. No matter which galaxy you observe from, it appears that distant galaxies are moving away. This realization changed our understanding of the cosmos forever. The universe was not static and eternal in the way people once imagined. It had a history. It had evolved over time, and if the universe is expanding today, then in the distant past, everything must have been closer together. Astronomers began to trace this idea backward in time, like slowly rewinding a cosmic film. Galaxies would move closer and closer together. The temperature of the universe would rise, matter would become denser, until eventually all of space would lead back to a much smaller and hotter state billions of years ago, an early phase of cosmic history that would later become known as the Big Bang. Yet even with this powerful idea, many quiet mysteries remained. If space is expanding, what exactly is it expanding into? Does the universe have an edge somewhere far beyond our telescopes? Could someone in an impossibly advanced spacecraft travel forever? and eventually reach the outer limit of everything that exists? Or would the universe simply continue endlessly without a final boundary? These questions slowly bring us toward the deeper puzzle hidden behind the expansion of the cosmos. A puzzle that feels almost dreamlike when you think about it carefully. The more scientists study the universe, the more it begins to resemble something far stranger than a simple explosion in empty space. Something closer to an ever-stretching fabric of reality itself. Tonight, as the mind begins to slow and the body relaxes, imagine the universe not as a violent event, but as a gentle and silent unfolding. Galaxies drifting apart across unimaginable distances, light traveling for billions of years before quietly reaching a telescope on a small planet orbiting an ordinary star. And somewhere within that vast expanding darkness, a simple question continues to drift through the thoughts of astronomers and dreamers alike. If the universe keeps expanding forever, could anyone ever reach its end? Or is the idea of an edge itself just another illusion created by the limits of human imagination? When people first hear that the universe is expanding, they often imagine something dramatic. A gigantic explosion that happened long ago, sending galaxies flying outward through empty space. This image is understandable, because explosions are familiar to us. Fireworks burst outward in all directions. Fragments scatter across the sky, and everything seems to move away from a central point. But the expansion of the universe is not exactly like that kind of explosion. In fact, the difference between these two ideas is one of the most fascinating and subtle concepts in modern astronomy. Because the universe is not expanding into empty space the way fragments move through the air. Instead, space itself is stretching. To understand this more clearly, imagine a calm night where you are drawing small dots on the surface of a balloon using a marker. Each dot represents a galaxy somewhere in the universe. At first, the balloon is small and the dots sit close together. Now slowly begin inflating the balloon. As the surface stretches, the dots move farther away from each other. What is interesting is that none of the dots are actually traveling across the surface of the balloon. They remain fixed in place on the rubber, yet the distance between them increases because the surface itself is expanding. Every dot sees the others drifting away, and the farther apart two dots are, the faster the distance between them grows. This is very similar to what astronomers observe in the real universe. Galaxies are not simply racing through space from a single center point. Instead, the fabric of space between galaxies slowly stretches over time, carrying galaxies apart with it. The universe behaves more like the expanding surface of the balloon than like a firework explosion. Another interesting detail appears when we ask where the center of this expansion might be. In a normal explosion, there is always a clear center, a location where the blast began. But when scientists look at the universe, something very unusual happens. Every galaxy appears to see the same pattern of expansion. From Earth, it looks like distant galaxies are moving away from us in all directions. But if someone were living in a distant galaxy billions of light years away, they would see the exact same thing. Galaxies around them would also appear to be drifting away. The expansion does not seem to have a single central location. This leads to a surprising realization. The expansion of the universe does not have a center inside the universe itself. Instead, the expansion happens everywhere at once. Every region of space stretches in the same quiet way, which means there is no special point where the universe began spreading outward from. If we return to the balloon example, the center of the expansion is not located on the surface where the dots are drawn. The center would actually exist somewhere inside the balloon, a place that does not exist within the two-dimensional surface itself. In a similar way, our three-dimensional universe may not contain a center that can be located within space. This idea can feel strange at first, because human intuition is built from everyday experiences. We are used to objects moving through space. We are used to edges and boundaries. But the expansion of the universe introduces something far more subtle: the stretching of space itself. Another quiet consequence of this expansion is that extremely distant galaxies can appear to move away faster than the speed of light. This might sound impossible at first, because nothing is supposed to travel faster than light. But the galaxies are not actually racing through space that quickly. Instead, the space between us and them is expanding. Imagine standing on a long moving walkway at an airport, while the floor itself begins stretching longer and longer. Even if you remain standing still, the distance between you and the far wall would increase faster and faster as the walkway grows. Something similar happens on cosmic scales where the distances themselves are changing. Over billions of years, this stretching has slowly increased the size of the universe. Galaxies that were once much closer together now lie separated by enormous distances. Light from the most distant ones travels for unimaginable stretches of time before reaching our telescopes. And as astronomers continue studying this gentle expansion, a deeper question begins to form. If space can stretch and grow larger over time, could it stretch forever without limit? Or might there be some hidden structure to the universe that eventually brings us to an edge? For now, the universe appears vast beyond easy comprehension, filled with billions of galaxies drifting slowly apart in a quiet cosmic tide. But whether this ocean of space has a distant shoreline or continues endlessly in every direction remains one of the most calming and mysterious questions the human mind can explore. And as the night becomes quieter and thoughts begin to slow, it is peaceful to imagine the universe not as a chaotic explosion, but as a silent and steady expansion, a gentle stretching of space itself, carrying galaxies farther into the darkness, while somewhere on a small blue planet, a curious mind wonders how far this expansion might truly go. Long before galaxies existed, long before stars began to shine, the universe was a very different place, a place where everything that would ever become stars, planets, oceans, mountains, and even the atoms in our own bodies existed in a state that was unimaginably hot and incredibly dense, not crowded in one small corner of space, but compressed into a universe that was itself much smaller than it is today. When scientists describe the early universe, they are not describing an explosion that happened somewhere in space. Instead, they are describing a time when the entire universe was compressed into a far smaller volume and then began expanding. The expansion did not throw matter outward into empty darkness. Rather, the darkness itself began stretching, carrying energy and matter with it. In those earliest moments, the universe was filled with an intense glowing energy. Temperatures were so high that atoms could not exist. Particles collided constantly in a bright sea of radiation. Space itself was young and rapidly changing, and time had only just begun its long, quiet flow forward. One of the most fascinating ideas scientists developed to explain the early universe is something called cosmic inflation, a brief moment very early in cosmic history when the universe expanded extremely quickly, faster than it has ever expanded since. During this period, space itself stretched at an incredible rate, smoothing out irregularities and spreading tiny fluctuations across enormous distances. To imagine this, it can help to picture a small wrinkle in a sheet of fabric that suddenly gets pulled tightly from every direction. The wrinkle becomes stretched out and flattened. In a similar way, the early expansion of the universe stretched the structure of space itself, leaving behind faint patterns that scientists can still detect billions of years later. These patterns exist in something known as the cosmic microwave background, a faint glow that fills the universe in every direction. It is the leftover light from a time when the universe had cooled enough for atoms to finally form, around 380,000 years after the beginning of cosmic expansion. Before this moment, the universe was filled with a thick fog of charged particles and light constantly bouncing around. But when atoms formed, the fog suddenly cleared and light was finally able to travel freely across space. That ancient light has been traveling ever since, slowly stretching along with the expansion of the universe. Today, astronomers can detect this faint glow using sensitive instruments, and when they map it carefully, they see tiny temperature variations spread across the sky, incredibly subtle patterns that reveal the structure of the early universe. like gentle ripples frozen into the background of space. These ripples would eventually grow under the influence of gravity. Over millions, and then billions of years, they slowly gathered matter together, forming the first stars and galaxies, enormous structures that now fill the universe with light. Yet even while stars were forming and galaxies were assembling themselves, the expansion of space never stopped. Distances between galaxies continued to grow, slowly and steadily stretching the cosmic landscape. If we imagine traveling backward in time through this process, everything becomes closer together. Galaxies cluster tighter. Stars approach one another. Eventually, the universe becomes a dense glowing fog again. And earlier still, it becomes an incredibly hot ocean of energy, where the familiar structures of matter cannot exist. This is not a single location that can be pointed to in space. It is a moment in time that happened everywhere at once. Every region of the universe was once part of that earlier dense state, which leads to a fascinating realization. The Big Bang was not an explosion that occurred at one point in space. Instead, it was the beginning of the expansion of space itself, a moment when the universe started growing larger, everywhere simultaneously. This idea changes how we think about traveling through the universe. If the Big Bang happened everywhere, then no matter how far we travel, we will never reach a location where it happened, because every point in space shares the same origin in time. And as the universe continues expanding today, the distances between the largest structures slowly increase. Galaxies drift farther apart like distant islands carried away on a calm cosmic ocean. Some galaxies are already so far away that their light will never reach us, because the expansion of space stretches the distance faster than the light can travel toward us, meaning parts of the universe are quietly slipping beyond our ability to ever observe them. The universe, therefore, has a kind of visible horizon, not an edge made of matter or walls of darkness, but a limit created by the finite speed of light and the long history of cosmic expansion. Beyond that horizon, there may be countless galaxies, perhaps structures larger than anything we have seen, but their light has not yet had enough time to reach Earth during the age of the universe. And as the mind drifts slowly through these ideas, it becomes possible to imagine the early universe as a calm beginning rather than a violent blast. A moment when space itself began stretching like a slowly expanding fabric, unfolding across billions of years into the vast and quiet cosmos we observe tonight. As the universe continued expanding over immense stretches of time, the first galaxies slowly formed, enormous collections of stars bound together by gravity, rotating quietly through space like vast luminous cities scattered across the darkness. And once these galaxies began appearing, something very interesting started to happen on the largest scales of the cosmos. When astronomers observe distant galaxies through powerful telescopes, they notice a consistent pattern. Almost every galaxy outside our local neighborhood appears to be moving away from us. The farther away a galaxy is, the faster it seems to be receding. This observation became one of the most important clues about the nature of the expanding universe. At first, this idea can sound a little strange, because it almost makes it seem as if Earth or our galaxy sits at the center of everything. But this is not the case at all. The same observation would appear true from nearly any galaxy in the universe, no matter where an observer might be located. To understand this more easily, imagine standing in the middle of a large field covered with evenly spaced lanterns. Now imagine the ground beneath the lanterns slowly stretching in every direction. Each lantern stays attached to the ground where it is placed, but the distances between them gradually increase as the ground expands. From the position of any single lantern, all the others would appear to be moving away. The farther lanterns would separate faster simply because there is more ground stretching between them. This simple picture helps explain why astronomers observe galaxies drifting apart. This relationship between distance and speed became known as Hubble's law, which describes the idea that galaxies twice as far away tend to move away roughly twice as fast. and galaxies 10 times farther can appear to recede even more rapidly as space itself stretches between them. What makes this even more fascinating is that galaxies are not actively flying through space like rockets. Instead, they are mostly sitting still within their local regions of space, while the fabric of space itself slowly expands, carrying them along with it. However, gravity still plays an important role locally. Galaxies that are relatively close together can remain bound by their mutual gravitational pull, forming clusters and groups where expansion does not tear them apart. Our own galaxy, the Milky Way, is part of a small group of galaxies known as the local group. And within this group, the effects of gravity are stronger than the gentle stretching of space, meaning some galaxies actually move toward each other rather than away. One of these galaxies is the Andromeda Galaxy, a massive spiral galaxy that is slowly drifting closer to the Milky Way over billions of years. Eventually, the two galaxies are expected to merge in a slow cosmic dance of stars, creating a new larger galaxy in the distant future. But beyond the gravitational influence of our local group, the expansion of the universe becomes more noticeable. Galaxy clusters separated by vast distances slowly drift apart as space expands between them. The farther we look into space, the farther back in time we are also looking. Because light takes time to travel, when we observe a galaxy a billion light years away, we are actually seeing it as it existed a billion years ago. This means astronomers can study how galaxies behaved at different times in the history of the universe simply by observing objects at different distances. Distant galaxies reveal a younger universe where structures were still forming and expansion was shaping the cosmic landscape. Over time, scientists noticed something even more surprising hidden in these observations. The expansion of the universe is not simply continuing at a steady pace. It appears to be accelerating, meaning the distances between distant galaxies are increasing faster as time goes on. This discovery introduced one of the greatest mysteries in modern cosmology, something scientists now call dark energy, a mysterious influence that seems to push space itself to expand more rapidly. But even without fully understanding this mysterious energy, one fact remains clear. The universe is not static, and it is not slowly settling down into stillness. Instead, it continues to grow larger as space stretches across unimaginable distances. If someone could watch the universe over billions of years, galaxies would appear to drift farther and farther apart. The cosmic web of matter slowly expanding like an immense three-dimensional fabric being gently pulled in every direction. Yet even as galaxies recede into the distance, a deeper question begins to take shape. If everything is moving away from everything else, does that mean the universe has a limit somewhere far beyond our view? Or could this expansion continue endlessly without ever reaching a final boundary? The answer is not as simple as traveling far enough to find a wall or an edge, because the expansion of space introduces a new kind of cosmic geometry, one where the shape of the universe itself becomes an important part of the story. And somewhere within that enormous structure, the possibility remains that the universe may not have an edge in the way our everyday intuition expects. The farther we look, the more the cosmos begins to resemble an endless landscape, where distances grow quietly larger, while the stars continue their slow journey through the expanding night. As astronomers continued observing the distant universe, they realized that the light arriving from faraway galaxies was carrying an extraordinary amount of information, not only about where those galaxies were located, but also about how the universe itself had been changing during the billions of years that light traveled across space. Light may seem simple when we see it with our eyes, but it behaves like a wave moving through space, and these waves can stretch or compress depending on motion and distance. When the source of light moves toward an observer, the waves become slightly compressed and shift toward the blue end of the spectrum. When the source moves away, the waves stretch and shift toward red. This gentle stretching of light is known as redshift, and it became one of the most powerful tools astronomers have for studying the expansion of the universe. Because the farther a galaxy is from us, the more its light appears stretched toward the red side of the spectrum. When astronomers pass the light from a galaxy through instruments that spread it out into a spectrum, they can see dark and bright lines that correspond to specific chemical elements. These patterns act like fingerprints of atoms such as hydrogen and helium. And when the lines appear shifted toward red, scientists know that the light waves have stretched during their journey. The fascinating part is that this stretching does not only happen because galaxies move through space. In the expanding universe, something deeper occurs. The space that light travels through is itself slowly stretching over time. And as the space expands, the wavelength of the light expands with it. Imagine drawing small waves on a rubber band using a pen. If the rubber band is pulled slowly apart, the waves drawn on its surface become longer and more stretched. The same quiet effect happens to light traveling through an expanding universe. The wave itself grows longer during the journey. Some of the light we observe tonight began traveling toward Earth billions of years ago, long before our planet even existed. During that enormous journey, the universe expanded continuously, stretching the light further and further. By measuring how much the light has stretched, astronomers can estimate how long it has been traveling and how far away its source must be. This allows scientists to build a three-dimensional map of the observable universe, filled with galaxies scattered across unimaginable distances. When we look deeper into space with larger telescopes, we see galaxies whose light has been traveling for billions of years, meaning we are observing them as they appeared in the distant past. The universe becomes a kind of time machine where distance and history become connected. The most distant galaxies we can currently observe show extremely large redshifts. Their light has been stretched many times longer than when it was originally emitted, revealing that the universe was much smaller when that light began its journey. This discovery provides one of the clearest pieces of evidence that the universe truly has been expanding over time. Not just locally, but across the entire cosmic landscape. Yet something even more remarkable appears when astronomers study extremely distant light sources. The expansion of the universe has stretched some wavelengths so dramatically that visible light can slowly transform into infrared or even microwave radiation by the time it reaches Earth. This is exactly what happened to the ancient glow known as the cosmic microwave background, the faint afterglow of the early universe that has been traveling through expanding space for nearly the entire history of the cosmos. Originally, that light was far more energetic and much hotter, but billions of years of expansion stretched it into the microwave radiation we detect today, filling the universe with a quiet background glow that arrives equally from every direction in the sky. This ancient light acts almost like a photograph of the universe when it was still very young, allowing scientists to study conditions from a time when galaxies had not yet fully formed. By analyzing these faint signals, researchers have been able to estimate the age of the universe to be around 13.8 billion years, a number that represents the long journey from the earliest stages of cosmic expansion to the present moment. And as astronomers continue measuring redshift in more distant galaxies, they see the same consistent story unfolding. The farther we look, the more strongly the universe reveals its long history of expansion. But this leads to a curious and calming question that slowly emerges from the data. If light has been traveling for billions of years, and the universe has been expanding the entire time, then there must be a limit to how far we can see. Beyond a certain distance, the light simply has not had enough time to reach us yet, since the beginning of cosmic expansion. This creates what scientists call the observable universe, a vast spherical region centered on our location containing all the galaxies whose light has had time to reach Earth since the beginning of the universe. Beyond that boundary, there may be more galaxies, and perhaps entire cosmic structures we will never see, hidden simply because their light is still on its long journey across expanding space. And as thoughts begin to slow with the quiet rhythm of these ideas, it becomes peaceful to imagine light itself drifting slowly through the cosmos for billions of years, stretching gently as the universe expands, carrying with it the silent story of distant galaxies moving farther into the deep and ever-widening darkness of space. As astronomers continued studying the expansion of space and the stretched light arriving from distant galaxies, they slowly realized that our view of the universe is naturally limited, not by the power of telescopes alone, but by the age of the universe itself. Because light travels at a finite speed, and the universe has existed for a specific amount of time, every signal that reaches Earth today has spent years, centuries, or even billions of years traveling through space before arriving here. The light from the sun takes about 8 minutes to reach our planet. The light from nearby stars can take several years, and the light from distant galaxies may travel for billions of years before entering a telescope. Because of this simple fact, there is a maximum distance from which light could have reached us since the beginning of cosmic expansion. Beyond that distance, the light is still traveling and has not yet arrived. This creates a natural boundary to what we can observe. Astronomers call this region the observable universe, a vast spherical volume of space centered around our location, containing everything whose light has had enough time to reach Earth during the roughly 13.8 billion years since the early universe. At first glance, someone might assume that the observable universe should therefore have a radius of about 13.8 billion light years, since light travels 1 light year each year. But the situation is more subtle because the universe has been expanding while that light was traveling. When the light from extremely distant galaxies first began its journey, those galaxies were much closer to our region of space than they are today. During the billions of years that the light traveled, the universe continued expanding, stretching the distance between us and the source. Because of this expansion, the galaxies that emitted the most ancient light we observe today are now located much farther away than the distance the light actually traveled. The present distance to the edge of the observable universe is estimated to be about 46 billion light years in every direction. This means the observable universe forms an enormous sphere nearly 92 billion light years across, containing hundreds of billions of galaxies, each one filled with billions of stars and perhaps countless planets. Even though this region is unimaginably vast, it may still represent only a small portion of the entire universe, because the observable universe is simply the part we can currently see from our location and our moment in cosmic history. If the universe continues infinitely beyond this horizon, there could be regions of space that are forever invisible to us, not because they are hidden behind objects or darkness, but because their light will never reach our location due to the expansion of space. Imagine standing on the shore of a calm ocean at night. The horizon limits how far you can see across the water. Beyond that line, the ocean continues, but your view cannot extend any farther. The observable universe works in a somewhat similar way. However, the cosmic horizon is not fixed in place. As time moves forward, light from slightly more distant regions has time to reach us, slowly expanding the volume of space we are able to observe. Yet the accelerating expansion of the universe introduces another interesting effect. Some extremely distant galaxies are now moving away so quickly due to the expansion of space that the light they emit today will never reach Earth at all. Their earlier light may still be on its way toward us, allowing us to observe them as they existed billions of years ago. But any new light they emit now is carried away by the expansion faster than it can travel toward us. In this sense, parts of the universe are gradually disappearing beyond our cosmic horizon, not vanishing physically, but becoming permanently unreachable to observation. This idea introduces a calm and slightly mysterious perspective on the cosmos. There may be vast regions of the universe that we will never be able to see, no matter how advanced our technology becomes. Somewhere beyond the observable horizon, there could be galaxies forming stars, planets circling distant suns, perhaps even civilizations looking back toward their own cosmic horizon, wondering about the unseen regions beyond. The observable universe, therefore, represents not the full universe, but simply the portion of cosmic reality that light has had time to reveal to us so far. And as the universe continues expanding across unimaginable spans of time, the structure of this observable region will slowly change. Galaxies will drift farther away, and the distant cosmos will gradually become darker as fewer and fewer galaxies remain visible. Yet for now, we exist during a remarkable era of cosmic history, a time when the universe is old enough for complex structures like galaxies and life to exist, but still young enough that we can observe vast portions of the cosmos stretching outward in every direction. This quiet window into the universe allows us to explore deep questions about the nature of space itself, including the possibility that beyond everything we can see, the universe may continue far beyond our horizon, perhaps endlessly expanding without ever revealing a final boundary. And somewhere within that immense unseen expanse, the question remains suspended like a distant star. If the universe is expanding everywhere, and our view is limited by the journey of light, then what would it truly mean to reach the end of the universe? And would such an end even exist at all? Once the idea of the observable universe becomes clear, another deeper thought begins to emerge. The region we can observe is not necessarily the entire universe. It is simply the portion of space whose light has had enough time to reach us since the beginning of cosmic expansion. This distinction may seem small at first, but it changes the scale of the cosmos in a profound way, because the observable universe is limited by time and distance, while the full universe could extend far beyond anything we will ever see. Imagine standing in a vast, foggy landscape at night with a lantern in your hand. The light from the lantern illuminates only a certain distance around you. Within that circle, you can see trees, hills, and rocks clearly. But beyond the edge of the light, the landscape may continue endlessly into the darkness. Your illuminated circle does not represent the entire landscape. It only represents the region that your light is capable of revealing. In a similar way, the observable universe is simply the region of cosmic space that light has been able to reveal to us so far. Beyond that boundary, there may be more galaxies, more stars, and perhaps structures larger than anything we have yet observed. But their light is still traveling through space and has not reached our telescopes. What makes this idea particularly fascinating is that the universe does not place us in a special location. Observers in distant galaxies would also experience their own observable universe centered around them, with their own horizon beyond which light has not yet arrived. From their perspective, our galaxy might lie somewhere near the edge of what they can observe, while beyond their horizon there would also be regions forever hidden from their view. This means that across the entire universe, there could be countless observable spheres overlapping and extending outward from different locations, each one revealing a slightly different portion of the cosmic landscape. In this way, the observable universe is not a fixed object, but a perspective shaped by the location of the observer and the age of the universe itself. Scientists have attempted to estimate the possible size of the entire universe using observations of cosmic structure and the curvature of space. And many current models suggest that the universe could be vastly larger than the observable region, possibly even infinitely large. If the universe is truly infinite, then the observable universe would represent only a tiny fragment of a much larger reality, like a small window cut into an endless wall. Yet even if the universe is not infinite, it could still extend far beyond our horizon, perhaps hundreds or thousands of times larger than the region we can see. This idea introduces a peaceful kind of humility into our understanding of the cosmos, because no matter how powerful our telescopes become, there may always remain regions of the universe that lie forever beyond observation. The light from those regions may still be traveling through space, slowly crossing unimaginable distances, perhaps one day reaching galaxies far from ours, but never arriving here. It is also possible that some regions are receding from us so quickly due to the expansion of space that their light will never be able to reach us at all. even given unlimited time. This means that the universe contains not only distant places, but also permanently unreachable ones. Areas of cosmic reality that exist, but remain hidden behind the limits imposed by expansion and the speed of light. As scientists think about this distinction between the observable universe and the entire universe, they begin to ask a new question. If the universe extends far beyond what we can observe, could it have a physical edge somewhere? A boundary where space itself ends? Or could the universe instead behave more like a surface without edges, something that continues endlessly without ever reaching a final border? To answer that question, researchers look not only at galaxies and light, but also at the geometry of space itself. Because the shape of the universe may determine whether an edge could exist, the idea that space itself might have a shape is one of the most surprising discoveries of modern physics, because space is not simply an empty container where things happen. It can bend, curve, and stretch under the influence of matter and energy. This means the universe may have a global structure that is difficult to imagine using everyday intuition, something that might allow it to expand forever without requiring a physical boundary. And as thoughts slowly settle into the calm rhythm of the night, it becomes possible to picture the observable universe as a glowing bubble of visibility floating within a much larger cosmic sea, a region illuminated by ancient light, while the rest of the universe continues silently beyond the horizon, waiting perhaps forever beyond the reach of our view. When people imagine the universe, they often picture it as an enormous space that eventually ends somewhere, perhaps with a distant boundary or a wall beyond which nothing exists. This idea feels natural, because nearly everything we experience in everyday life has edges. Rooms have walls, oceans have shores, and even the sky appears to meet the horizon far away. But when scientists study the structure of the universe, they begin to realize that space may not behave in the same way as ordinary objects. The universe might not need an edge at all, and understanding why requires thinking about the geometry of space itself. One of the most helpful ideas for imagining this comes from the surface of a planet. If you stand anywhere on Earth, the ground appears flat and endless around you. Yet the planet itself is actually curved into a sphere. If someone began walking in one direction across the Earth, they would never encounter an edge of the surface. Instead, they would eventually circle the entire planet and arrive back where they started. The surface is finite, but it has no boundary. This simple example reveals something important. It is possible for a space to be limited in size yet still have no edges, because the geometry of that space curves back on itself. Scientists began wondering if something similar could happen with the universe. Perhaps the universe could be curved in a way that allows it to be large, but still without any outer boundary. In the early 20th century, the theory of general relativity introduced the idea that space and time together form a flexible structure known as spacetime. And this structure can bend or curve in the presence of matter and energy. Large objects such as stars and galaxies cause spacetime to curve slightly, which is why gravity can bend the path of light or influence the motion of planets. But the curvature of space does not only occur locally around stars and galaxies, it may also exist on the largest scales of the universe itself, shaping the overall structure of cosmic space. If the universe has positive curvature, then its geometry would resemble the surface of a sphere, except in 3 dimensions instead of 2. In such a universe, traveling far enough in one direction could eventually bring you back toward your starting region. However, this journey would require traveling distances far greater than the observable universe, making it impossible with any technology we can currently imagine. Another possibility is that the universe has negative curvature, meaning space bends outward in a shape somewhat similar to a saddle surface. In this type of geometry, the universe could continue expanding endlessly without looping back on itself. A third possibility is that the universe is geometrically flat on the largest scales, meaning that space extends evenly without significant curvature. This does not necessarily mean the universe is infinite, but it would allow it to grow extremely large. Astronomers have spent decades measuring the structure of the universe to determine which of these possibilities is correct, and observations of the cosmic microwave background suggest that the universe is remarkably close to flat. This means that on very large scales, the geometry of space appears almost perfectly balanced, not strongly curved inward or outward. Yet even a nearly flat universe could still be finite or infinite, depending on its deeper structure. And determining that exact structure remains one of the most challenging questions in cosmology. If the universe is infinite, then there would be no edge to reach, no final boundary beyond which space stops existing. The universe would simply continue forever in every direction. But even if the universe is finite, it might still have no edge in the ordinary sense, much like the surface of the Earth where travel can continue indefinitely without encountering a border. This idea can feel surprisingly peaceful when imagined slowly. A universe without walls or endings, where space continues smoothly across unimaginable distances. Traveling through such a universe would not reveal a sudden boundary or a cosmic cliff. Instead, the journey would simply continue through more galaxies, more clusters, and more regions of expanding space. And as the mind settles into this quiet perspective, it becomes easier to imagine the cosmos, not as a box with limits, but as a vast, continuous landscape where the concept of an edge may not apply at all. Somewhere within that enormous structure, galaxies continue their slow movement through expanding space, and the universe stretches gently outward, while the question of its true shape remains one of the most calming and mysterious ideas ever explored by human curiosity. As scientists explored the geometry of space and the expansion of the cosmos, another possibility slowly became more serious in the minds of many cosmologists. The universe might not only be extremely large, it might actually be infinite. The idea of infinity can feel difficult to grasp because our everyday experiences always involve limits. Every road eventually ends. Every journey has a destination. Every object occupies a certain space and no more. Yet mathematics allows the possibility of structures that continue forever without reaching a boundary. If the universe is infinite, it would mean that space extends endlessly in every direction. There would be no outer wall of the cosmos, and no final region where existence stops. Galaxies would continue appearing farther and farther away without ever reaching a final edge. From our perspective, this infinite universe would still appear limited by the observable horizon, because light from extremely distant regions would not have had enough time to reach us yet. So our view would always remain confined to a finite bubble of visibility. But beyond that bubble, the universe could continue endlessly, filled with galaxies, stars, and cosmic structures stretching across distances so vast that even light traveling for trillions of years would never reach the farthest regions. In such a universe, the expansion of space becomes even more fascinating, because it would not be an expansion into something else. Instead, the entire infinite fabric of space would simply be stretching, increasing the distances between galaxies everywhere at once. An infinite universe expanding over time means that the average distances between galaxies would slowly grow larger, while the overall universe remains without boundaries. Some scientists even consider an intriguing consequence of infinity. If space truly extends forever, and matter is distributed somewhat evenly across the cosmos, then somewhere incredibly far away, there could exist regions that look very similar to our own. Given enough distance, the combinations of matter might repeat, creating galaxies similar to the Milky Way, stars similar to our Sun, and perhaps even planets with environments resembling Earth. The distances required for such repetitions would be unimaginably enormous, far beyond the observable universe. But the possibility arises naturally in an infinite cosmos. This thought can feel both mysterious and strangely calming. The universe becoming an endless landscape of cosmic variety, where similar patterns may appear again and again across distances too vast to ever explore. However, scientists remain cautious about declaring the universe infinite with certainty, because observations can only measure what lies within the observable universe. When astronomers examine the cosmic microwave background and the distribution of galaxies, they can estimate the curvature of space, and current measurements suggest that the universe appears extremely close to flat on the largest scales. A perfectly flat universe could indeed be infinite, but it could also be finite in ways that are difficult to detect. For example, space might wrap around itself in complex ways that only become noticeable over distances larger than the observable universe. In such a scenario, traveling far enough through space might eventually bring you back to your starting point from another direction, similar to walking around the Earth but in three-dimensional space. Because our observations are limited to a finite region, scientists cannot yet determine with absolute certainty whether the universe is truly infinite or simply unimaginably large. For now, both possibilities remain open, and each carries its own fascinating implications for the nature of reality. If the universe is finite but unbounded, it would resemble a vast curved structure where space eventually loops back on itself. If the universe is infinite, it would continue endlessly with no repetition of boundaries, only more and more space stretching outward forever. Either way, the expansion of the universe continues quietly across billions of light years, slowly increasing the distance between galaxies as cosmic time moves forward. And somewhere in that enormous expanding structure, the idea of reaching the end of the universe begins to feel more complicated than it first appeared. Because if the universe is infinite, there would be no end to reach at all. Instead, the farther someone traveled, the more universe would simply appear ahead of them. New galaxies emerging in the distance, while the ones behind slowly fade into the expanding darkness. This possibility transforms the universe into something that feels almost dreamlike in scale. A cosmic landscape without borders, where expansion continues silently and endlessly across the deep and quiet fabric of space. Once the mind begins imagining the universe as something vast and expanding, a natural question quietly appears. What would happen if someone actually tried to travel to the end of the universe? If a spacecraft could move continuously through space for millions or even billions of years, would it eventually reach a boundary where everything stops? At first, this idea seems simple. If the universe has an edge, then a long enough journey should eventually reach it. But when scientists carefully examine how space behaves, the situation becomes far more unusual than a simple voyage across distance. The first difficulty appears when we remember that the universe is expanding. The distances between galaxies are slowly increasing over time because the fabric of space itself is stretching, meaning that even while traveling forward, the universe ahead would also be slowly expanding. Imagine trying to walk across an enormous moving walkway that is stretching longer as you move. Each step takes you forward, but the distance to the far end keeps increasing. The faster the walkway stretches, the more difficult it becomes to ever reach the end. Something similar happens on cosmic scales. If a traveler moved through space toward distant galaxies, the expansion of space could increase the distance to those galaxies while the traveler is still moving. For nearby regions, gravity can keep galaxies relatively stable with respect to each other, which is why galaxies inside clusters remain bound together despite the expansion of the universe. But beyond those clusters, the expansion becomes more noticeable, and over extremely large distances, it dominates the motion of galaxies themselves. There is also a fundamental speed limit in the universe, the speed of light. Nothing that carries information or matter can travel faster than light through space. This rule places a natural limit on how quickly a spacecraft could explore the cosmos. Because of this limit, many galaxies that exist today are already receding from us so quickly, due to the expansion of space, that even light traveling from them right now will never reach Earth in the future. This means there are regions of the universe that are permanently unreachable from our location, not because they are hidden by obstacles, but because space itself is expanding between us too rapidly. If someone attempted to travel toward these extremely distant regions, the expansion would continue stretching the distance ahead of them, creating a kind of moving horizon that retreats faster than they could approach it. Over time, more and more galaxies would slowly disappear beyond this cosmic horizon, their light becoming too stretched and too distant to ever reach the traveler. In a universe where expansion continues, accelerating, this effect becomes even stronger. Distant galaxies gradually fade from view as the observable region becomes smaller relative to the entire universe. This does not mean those galaxies vanish. They continue existing in their own regions of space, but they become separated from us by distances that light itself can no longer cross. Because of this expanding horizon, the idea of traveling to the edge of the universe becomes deeply complicated. Even with a spacecraft capable of traveling close to the speed of light, the expansion of space would still shape what regions of the cosmos could ever be reached. And if the universe has no edge at all, then the journey would never reveal a final boundary. Instead, it would simply continue through more and more galaxies scattered across an ever-expanding cosmic landscape. The farther someone traveled, the more distant structures would appear ahead, while the ones behind slowly drift farther away. Even after billions of years of travel, the traveler might still find themselves surrounded by galaxies and stars, with no sign of a cosmic wall or final limit. This perspective reveals that reaching the end of the universe may not be like reaching the end of a road or the shore of an ocean. The universe may not contain such an ending at all. Instead, it may behave more like an endless expanding terrain, where every direction continues into more space. And as thoughts move slowly through these possibilities, it becomes easier to imagine the universe not as a destination, but as a continuous journey. Galaxies drifting quietly apart, while the fabric of space stretches across distances so vast that the idea of an edge begins to dissolve into the calm mystery of the expanding cosmos. When imagining a journey across the universe, it is natural to picture traveling in a straight line, pointing a spacecraft in one direction and continuing forward endlessly through space, passing stars, galaxies, and distant clusters while moving toward the unknown edges of the cosmos. But the idea of moving in a perfectly straight line becomes more complicated when scientists consider the deeper structure of space-time. Because space itself may not behave like a flat, empty grid, extending infinitely in every direction. According to modern physics, space and time are woven together into a structure called space-time, and this structure can bend and curve under the influence of matter and energy, meaning that what appears to be a straight path may actually follow the curvature of space-time itself. A helpful way to imagine this comes from thinking about the surface of the Earth. If someone begins walking across a large flat field, the path may appear perfectly straight, but on the scale of the entire planet, that straight path is actually following the curved surface of the Earth. Airplanes flying across the planet often follow routes that look curved on a flat map, yet those routes are actually the shortest straight paths across the curved surface of the globe. In physics, these natural paths are called geodesics. They represent the straightest possible routes through curved space. Light itself follows these paths through space-time, which is why the presence of massive objects like stars and galaxies can bend the path of light passing nearby, an effect known as gravitational lensing. When astronomers observe distant galaxies whose light has been bent by massive clusters of matter, they are seeing direct evidence that space-time itself curves under the influence of gravity. If space can curve locally around stars and galaxies, then it may also possess curvature on the largest cosmic scales, shaping how long-distance travel through the universe would behave. In a universe with positive curvature, a traveler moving in what feels like a straight line could eventually return toward their starting region after crossing an enormous distance, similar to someone walking around the surface of the Earth. But if the universe has negative curvature, the traveler would continue moving through space that expands outward in a way that never loops back, with distances between paths slowly diverging over time. And if the universe is nearly flat on the largest scales, the traveler might move endlessly through space without encountering curvature strong enough to bring them back to their right starting point. Observations of the cosmic microwave background suggest that the geometry of the universe is extremely close to flat, which means that if the universe is curved, the curvature must be very subtle across enormous distances. Yet even a tiny amount of curvature could shape the structure of space across regions far larger than the observable universe. Because our measurements are limited to the part of the universe we can observe, scientists cannot yet determine with complete certainty how space-time behaves beyond that horizon. This uncertainty leaves open several possibilities for the ultimate shape of the universe, including geometries that allow space to be finite yet without edges, or geometries that allow space to extend forever. For a traveler attempting to cross the cosmos, this means that the idea of moving in a straight line might not lead to a final border. Instead, the path could follow the natural curvature of space-time through an expanding universe that continues far beyond anything we can observe today. Even if the traveler continued moving for billions of years, the journey might reveal only more galaxies and more cosmic structures emerging slowly from the darkness. Behind them, the galaxies they passed would drift farther apart as space expands, while ahead new regions of the universe would appear gradually within view. The path itself would not reveal whether the universe has an edge or not, because the geometry of space might prevent such an edge from existing in the way we normally imagine. And as the mind drifts through these ideas, it becomes possible to picture the universe as a vast curved landscape of space-time, where straight paths follow the hidden geometry of the cosmos, while galaxies continue their slow migration through the expanding night. As the understanding of space-time developed during the 20th century, scientists began realizing that the universe might possess a large-scale shape that is not immediately visible to our everyday perception, because space itself may be curved in ways that are subtle across vast distances. Curvature in space does not necessarily mean that the universe bends into a visible arc or dome. Instead, it means that the geometry of space behaves differently than the simple flat geometry people learn in school, where parallel lines never meet and the angles of a triangle always add up to 180 degrees. In curved space, these familiar rules can change slightly, and these small differences can reveal the hidden structure of the universe when astronomers measure enormous distances across the cosmos. To imagine curved space, it can help to return again to the surface of the Earth. If someone draws a triangle on a flat piece of paper, the angles of that triangle will always add up to exactly 180 degrees. But if a triangle is drawn across the curved surface of a sphere, the angles can add up to more than that. For example, a triangle drawn from the equator to the North Pole and back again can contain 390-degree angles, something impossible on a flat surface. This simple idea reveals that the geometry of a space depends on its curvature, and by measuring the geometry of very large cosmic triangles, astronomers can estimate how space behaves across the universe. Scientists do this by studying patterns in the cosmic microwave background, the faint radiation left over from the early universe, which contains tiny fluctuations that act like markers spread across the sky. By measuring the apparent sizes of these patterns, astronomers can determine whether the universe is curved inward, curved outward, or very close to flat. Current measurements suggest that the universe is extremely close to flat on the largest observable scales, meaning that its geometry behaves very similarly to the flat space described by classical mathematics. However, the word flat in this context does not necessarily mean the universe is infinite or without structure. It simply describes how distances and angles behave across the observable region. The universe could still be finite, but shaped in complex ways that are difficult to detect within the limits of our observations. Some theoretical models describe universes that wrap around themselves in higher dimensional shapes, allowing space to loop back in ways that would be nearly impossible to notice without traveling distances far larger than the observable universe. In such a universe, a traveler moving steadily in one direction might eventually return to their starting location after crossing unimaginable distances. Yet because the universe is expanding, this return journey could take longer than the entire current age of the cosmos. Another possibility is that the universe truly continues endlessly with almost perfect flatness, stretching forever without curvature large enough to cause space to loop back. In that case, the expansion of the universe would simply increase the distances between galaxies, while space itself continues extending outward without limit. Astronomers continue studying the cosmic microwave background and the distribution of galaxies to refine their measurements of cosmic curvature, searching for the faintest signs that might reveal the deeper geometry of the universe. Even the smallest deviation from perfect flatness could tell scientists something profound about the overall structure of space. For now, the evidence suggests that the universe is remarkably balanced, its geometry extremely close to flat across the region we can observe. This delicate balance allows the universe to expand smoothly across billions of light years without obvious signs of bending inward or outward. Yet beyond the observable horizon, the true shape of the cosmos remains unknown, hidden in regions whose light has not yet reached us. And as thoughts settle quietly into this idea, it becomes possible to imagine the universe as a vast cosmic fabric whose full shape stretches far beyond our view. A structure so enormous that even after billions of years of observation, we have only begun to glimpse the geometry of the space we inhabit. When scientists explore the possible shapes of the universe, one of the most intriguing possibilities is something known as a closed universe, a model in which the geometry of space curves inward in a way that eventually connects back to itself. In such a universe, space would be finite in size, but would not contain an outer edge or boundary, much like the surface of a sphere which has a limited area yet no borders, where the surface suddenly ends. To imagine this idea, it helps to think once again about traveling across the Earth. If someone begins walking in a straight line across the surface of the planet, they will never encounter a sudden edge where the ground disappears. Instead, they will continue moving across the curved surface until eventually returning to their starting location from the opposite direction. A closed universe would behave in a somewhat similar way, but in 3 dimensions instead of 2. Space itself would curve in such a way that extremely long journeys could eventually lead back toward the same region of space. If such a universe existed, a traveler moving endlessly in one direction might one day see familiar galaxies appearing ahead again after circling the entire cosmos. However, the scale required for such a journey would be so immense that it would likely exceed the entire observable universe many times over. This means that even if the universe were closed, its curvature could be so gentle across large distances that detecting it would be extremely difficult from our current position. Astronomers search for clues about this possibility by studying the large-scale structure of the universe and the patterns found in the cosmic microwave background. If the universe were strongly closed, certain patterns might appear repeated in different directions across the sky, suggesting that light has traveled around the universe and arrived from multiple paths. So far, no clear evidence of such repeating patterns has been found within the limits of current observations. Yet the idea of a closed universe remains scientifically possible because the curvature could be so slight that the full size of the universe extends far beyond what we can observe. In a closed universe, the expansion of space could still occur just as it does in our current models. Galaxies would continue drifting apart while the overall structure of space slowly grows larger. The universe could expand for billions or even trillions of years while still maintaining its curved geometry. Some earlier cosmological models suggested that a closed universe might eventually stop expanding and begin contracting again under the pull of gravity. In that scenario, the expansion would gradually slow until the universe reached a maximum size, and then began collapsing inward toward a hot, dense state once more. This hypothetical future was sometimes called the Big Crunch, a cosmic reversal where galaxies slowly move closer together again after billions of years of expansion. However, modern observations suggest that the expansion of the universe is currently accelerating due to the influence of dark energy, making a future collapse less likely according to current evidence. Even so, the concept of a closed universe continues to play an important role in cosmological research because it demonstrates that a universe can be finite without requiring an edge. This possibility challenges the everyday assumption that something must eventually end in order to have a limited size. Instead, the universe could be structured in a way that allows space to curve smoothly back on itself across enormous distances. For an observer traveling through such a universe, there would be no visible border marking the end of space. The journey would simply continue through more galaxies, clusters, and vast regions of expanding darkness. And after unimaginable spans of travel, the traveler might find themselves approaching familiar regions once again without ever encountering a cosmic wall or final boundary. This idea transforms the concept of the universe from something with edges into something more like a continuous cosmic landscape, curved gently through dimensions that stretch far beyond the limits of ordinary imagination. While some cosmological models describe a universe that curves inward and eventually connects back to itself, another possibility suggests the opposite kind of geometry, a structure known as an open universe where space curves outward instead of inward. In an open universe, the geometry of space would resemble a surface that continually expands outward without looping back on itself, something similar to a saddle shape that bends in opposite directions along different axes. This kind of curvature creates a universe where parallel paths slowly drift farther apart over enormous distances, and where traveling forever in one direction would never lead back to the same location. Instead, the journey would continue endlessly through new regions of space without ever encountering a boundary or returning to the starting point. An open universe therefore shares one important feature with the idea of an infinite universe. It does not contain a physical edge where space ends. Rather, it extends outward without limit. The difference lies in the geometry of that space. In an open universe, the structure of space-time subtly diverges outward, so that cosmic distances grow faster than they would in a perfectly flat universe. This curvature affects how galaxies are distributed across extremely large scales and how light travels through space over billions of years. Astronomers can study these effects by observing the cosmic microwave background and by mapping the distribution of galaxies across vast regions of the observable universe. If space had strong outward curvature, certain patterns would appear distorted in predictable ways when observed across the sky. For example, the apparent sizes of ancient structures in the cosmic microwave background would look slightly smaller than expected if space curved outward significantly. Measurements from space telescopes and observatories have shown that these patterns appear very close to what would be expected in a flat universe, meaning that if the universe is open, its curvature must be extremely subtle across the region we can observe. Even so, the open universe model remains important because it demonstrates that space could extend forever without looping back on itself. In such a universe, the expansion of space would continue indefinitely, with galaxies gradually drifting farther apart as time moves forward. Over extremely long periods of time, the large-scale structure of the universe would become more and more spread out. Clusters of galaxies would separate from one another across vast expanding distances, while stars within individual galaxies continue their quiet orbits. Eventually, distant galaxies could drift so far away that their light would become too faint and too stretched to detect, leaving each galaxy cluster increasingly isolated within its own region of space. The night sky in such a distant future might look very different from the one we see today. Instead of countless galaxies filling the depths of space, observers in a far future galaxy might see only the stars within their own system, while the rest of the universe slowly disappears beyond the cosmic horizon created by expansion. Yet even in this quiet future, The universe would continue existing beyond that horizon, stretching outward endlessly across regions that remain forever unreachable. An open universe, therefore, presents a calm and expansive picture of reality, one where space continues outward without limit, while the cosmic structures within it slowly drift farther apart. For anyone imagining a journey toward the end of the universe, such a model suggests that no final edge would ever appear. The traveler would continue moving through space while new regions slowly come into view ahead, but there would always be more universe beyond. This possibility transforms the question of reaching the end of the universe into something deeper, because the concept of an end may simply not apply to the structure of space itself. Instead, the universe may behave like an endlessly unfolding landscape, where expansion quietly carries galaxies farther apart, while the vast cosmic fabric stretches outward into distances that no journey could ever fully explore. Among the possible shapes the universe could have, one model has become especially important in modern cosmology. The idea that the universe may be geometrically flat on the largest observable scales, meaning the structure of space follows the familiar rules of Euclidean geometry, where parallel lines remain parallel, and the angles of a triangle add up to 180 degrees. At first, this may sound like the simplest possibility, but in reality, it carries profound implications about the balance of matter, energy, and expansion in the universe. In cosmology, the curvature of the universe is closely connected to something known as the critical density, a specific balance point that determines how strongly gravity and expansion influence the overall geometry of space. If the average density of matter and energy in the universe is greater than this critical value, space would curve inward, creating a closed universe where extremely long journeys might eventually loop back. If the density were lower than the critical value, space would curve outward, producing an open universe that expands forever with diverging geometry. But if the density is almost exactly equal to the critical value, then space becomes flat on large scales, neither bending inward nor outward in any significant way. Measurements made using satellites that observe the cosmic microwave background suggest that the universe is astonishingly close to this critical balance. The patterns seen in that ancient radiation appear at sizes that match what scientists would expect in a nearly flat universe. This discovery revealed something remarkable about the early history of the cosmos, because maintaining such precise balance over billions of years would normally be extremely unlikely. To explain this delicate balance, scientists developed the idea of cosmic inflation, an early period when the universe expanded extremely rapidly during the first tiny fraction of a second after cosmic expansion began. During this brief phase, space itself stretched enormously, smoothing out irregularities and pushing the geometry of the universe toward near-perfect flatness. In a sense, inflation acted like a powerful cosmic leveling process, stretching the structure of the universe so dramatically that any initial curvature became extremely small across the observable region. As a result, the universe we observe today appears very close to flat, even though it continues expanding across billions of light years. A flat universe does not necessarily mean the universe is infinite. It simply means the geometry of space behaves as though it were flat within the region we can measure. The full universe could still be finite, but wrapped in ways that are extremely difficult to detect, or it could truly extend forever in every direction. In a flat universe, traveling in a straight line would not gradually curve back toward the starting point as it might in a closed universe. Instead, the traveler would continue forward through space that appears consistent and evenly structured across vast distances. If the universe is infinite, this journey would reveal new galaxies endlessly without ever approaching a final boundary. And if the universe is finite but extremely large, the traveler might still spend billions of years moving through space without encountering any sign of an edge. Another important consequence of a flat universe is how expansion behaves over time. In earlier cosmological models, scientists expected that gravity from all the matter in the universe might gradually slow the expansion. But observations made in the late 20th century revealed that the expansion of the universe is actually accelerating. This acceleration appears to be driven by a mysterious influence known as dark energy, which seems to push space itself to expand more rapidly over time. In a flat universe dominated by dark energy, the expansion could continue indefinitely, gradually increasing the distance between galaxies, while cosmic structures become more widely separated. Over unimaginable spans of time, the large-scale structure of the universe could become increasingly quiet as distant galaxies drift beyond the cosmic horizon. Yet even as galaxies move farther apart, the universe itself would continue existing across vast regions of space. This possibility presents a universe that expands smoothly without boundaries, where space stretches across unimaginable distances while the idea of a final edge becomes less meaningful. Instead of a universe that ends somewhere far away, we may live in a cosmos where expansion continues quietly forever. The geometry of space balanced delicately between curvature and endless extension, and within that immense, flat cosmic landscape, galaxies continue their slow movement through time, while the universe itself grows larger with each passing moment, stretching the distances between everything in a calm and silent expansion that may never truly reach an end. As astronomers continued studying distant galaxies and measuring the expansion of the universe, another unexpected discovery slowly emerged from the data, something that changed our understanding of cosmic expansion in a surprising way. For many years, scientists assumed that the expansion of the universe might gradually slow down over time, because gravity from all the galaxies, stars, and matter in the universe should gently pull everything back toward each other. In this picture, the universe would still expand, but the rate of expansion would slowly decrease as gravity tried to resist the outward motion of space. But in the late 1990s, astronomers studying extremely distant exploding stars known as supernovae noticed something unusual. These supernovae act like cosmic distance markers because they produce a very predictable brightness when they explode. By measuring how bright they appear from Earth, scientists can estimate how far away they are. When researchers compared the distances of these supernovae with how much their light had been stretched by cosmic expansion, they expected to see signs that expansion had been slowing down. Instead, the results revealed the opposite. The distant supernovae appeared slightly dimmer than expected, which meant they were farther away than predicted by models where expansion slowed over time. The only explanation that fit the observations was that the expansion of the universe had been speeding up during the last several billion years. In other words, space itself was not just expanding, it was expanding faster and faster as time passed. This discovery introduced one of the greatest mysteries in modern cosmology, something scientists now call dark energy. Dark energy is not directly visible, and it does not behave like ordinary matter. Instead, it appears to be a property of space itself that causes space to expand. Unlike gravity, which pulls objects together, dark energy acts in the opposite way on cosmic scales, pushing space to stretch more rapidly as the universe grows larger. Today, scientists estimate that dark energy makes up roughly 70% of the total energy content of the universe. Ordinary matter, including stars, planets, and galaxies, accounts for only a small fraction of the total cosmic energy budget. Another portion is made up of dark matter, a mysterious form of matter that does not emit light, but whose gravitational influence helps shape galaxies and galaxy clusters. But dark energy dominates the long-term behavior of the universe because it influences the expansion of space itself. One of the most fascinating aspects of dark energy is that its effect becomes stronger as the universe grows larger. As space expands, there is simply more space where dark energy can exist, which means its influence increases over time. This leads to a kind of runaway expansion, where the universe continues stretching faster as billions of years pass. Galaxies that are already far away drift even farther apart, while new regions of space appear between them. Over incredibly long periods of time, this accelerating expansion could dramatically change the appearance of the universe. Distant galaxies may gradually move beyond our observable horizon as space stretches between them faster than their light can travel toward us. Observers in the far future might see a much darker universe where only nearby galaxies remain visible, while the rest fade beyond the reach of observation. Yet even in that quiet future, the universe itself would still exist beyond those horizons, continuing its expansion across enormous distances. Dark energy therefore plays a central role in the question of whether the universe has an end that could ever be reached. If expansion continues accelerating, then regions of the universe will become increasingly separated from one another, making long-distance travel across cosmic scales even more difficult. Instead of approaching a final boundary, a traveler might find that the universe ahead keeps expanding faster than they can cross it. The distances between galaxies would grow while the horizon of reachable space slowly shrinks relative to the total size of the cosmos. This realization deepens the mystery of the expanding universe, because it suggests that the true limits of space may not lie at a physical edge, but within the dynamic behavior of space itself. And as these ideas settle quietly into the mind, it becomes possible to imagine the universe as a vast expanding ocean of space-time, where galaxies drift apart across unimaginable distances, while the unseen influence of dark energy continues stretching the fabric of the cosmos further into the silent depths of space. Once astronomers realized that the expansion of the universe was speeding up rather than slowing down, a deeper question naturally appeared. Why would space itself begin expanding faster instead of gradually slowing under the pull of gravity? For most of cosmic history, gravity shaped the structure of the universe. Matter gathered together to form stars, galaxies, and clusters of galaxies. Enormous structures built slowly over billions of years through the steady attraction of mass. Gravity acts like a cosmic sculptor, pulling matter inward and shaping the large-scale architecture of the universe. Because of this influence, scientists originally expected that gravity would gradually slow the expansion of space, perhaps even bringing it to a halt after enough time had passed. But the discovery of accelerating expansion suggested that something else was influencing the large-scale behavior of the cosmos. This mysterious influence appears to act almost like a form of pressure built into space itself, something that gently pushes space-time outward rather than pulling it inward. Dark energy is the name given to this phenomenon, though the term does not describe exactly what it is. It simply describes the effect that scientists observe in the expansion of the universe. One way to imagine this effect is to picture the universe as an enormous elastic fabric that stretches slowly over time. If gravity alone shaped the expansion, the fabric would gradually stretch more slowly as the gravitational pull of matter resisted the expansion. But dark energy behaves as if the fabric itself contains an invisible tension that causes it to stretch more and more as it grows larger. As the universe expands, there is simply more space where this effect can act, allowing the expansion to accelerate over billions of years. In this sense, dark energy is not concentrated in galaxies or stars. It appears to exist everywhere throughout space. Even the emptiest regions between galaxies contain this mysterious energy that influences the overall expansion of the universe. Because dark energy acts across all of space, its influence becomes dominant as the universe grows larger. During the early universe, matter and radiation were much denser, and their gravitational influence played the dominant role in shaping cosmic expansion. But as billions of years passed and the universe expanded, matter became more spread out while dark energy remained constant throughout space. Eventually, dark energy began to dominate the large-scale behavior of the universe, leading to the accelerated expansion astronomers observe today. This transition occurred several billion years ago and continues shaping the future evolution of the cosmos. If the influence of dark energy remains constant, the universe will continue expanding faster and faster as time moves forward. Galaxies that are currently visible from Earth will slowly drift farther away across billions of years, Some will eventually move beyond the cosmic horizon where their light can no longer reach us. Future observers living in distant epochs of cosmic history might look into the sky and see far fewer galaxies than we see today. The rich tapestry of distant galaxies visible through modern telescopes could slowly fade as expansion carries them beyond the limits of observation. Yet within each galaxy, stars would still shine, and planetary systems could continue forming, local regions of the universe remaining active, even while the large-scale structure becomes more isolated. The accelerating expansion, therefore, does not destroy galaxies or stars directly. Instead, it quietly increases the distances between the largest cosmic structures. Clusters of galaxies become isolated islands separated by expanding seas of empty space. Over immense spans of time, the universe could become a collection of widely separated cosmic regions, each surrounded by darkness, stretching across unimaginable distances. This long-term future adds another layer to the question of reaching the end of the universe. If expansion continues accelerating, then even the journey toward extremely distant regions becomes increasingly difficult. The farther one attempts to travel, the faster the space ahead may stretch. Instead of approaching a cosmic boundary, the traveler might discover that the universe itself continues unfolding faster than the journey can progress. And so the idea of a final edge becomes even more uncertain, because the structure of space itself may prevent such an edge from ever being reached. The universe may simply continue expanding quietly across time, while galaxies drift farther apart and the vast cosmic fabric stretches deeper into the silent darkness beyond the limits of human imagination. As the expansion of the universe continues accelerating under the influence of dark energy, astronomers have begun to imagine what the distant future of the cosmos might look like. And one of the most fascinating possibilities is that many of the galaxies we see today will eventually disappear from view. This does not mean those galaxies will be destroyed or cease to exist. Instead, they will slowly move beyond the cosmic horizon created by the expansion of space itself. The universe is filled with galaxies scattered across enormous distances, and today, powerful telescopes allow us to observe hundreds of billions of them across the observable universe. Some appear as faint smudges of light that have traveled for billions of years before reaching Earth. But the expansion of the universe means that the distances between these galaxies continue increasing over time. As space stretches, the light, traveling between distant regions, must cross larger and larger distances. Eventually, some galaxies become so far away that the expansion of space carries them outward faster than the light they emit can travel toward us. When this happens, new light from those galaxies can no longer reach Earth. We may still see the light they emitted long ago during earlier stages of the universe, but over time, even that ancient light becomes increasingly stretched and faint as it crosses expanding space. Gradually, the galaxies fade from visibility as their light redshifts into longer and longer wavelengths. Given enough time, those wavelengths could stretch beyond the limits of our instruments, effectively removing those galaxies from our observable universe. From our perspective, they would slowly vanish into the darkness, not because they disappeared physically, but because the expansion of space carried them permanently beyond our cosmic horizon. This process will unfold extremely slowly across billions and trillions of years. Human lifetimes are far too short to notice these changes directly, but over immense cosmic timescales, the structure of the observable universe will gradually transform. Galaxies that are currently visible across vast distances will drift farther away, while new light from them becomes increasingly difficult to detect. Eventually, only galaxies that remain gravitationally bound within our local region of space will remain visible. Our Milky Way galaxy is part of a small gravitational family known as the Local Group, which includes nearby galaxies such as Andromeda and several smaller companions. Because gravity binds these galaxies together, they are not carried apart by the expansion of the universe. In fact, the Andromeda Galaxy is slowly moving toward the Milky Way and will likely merge with it several billion years in the future. Long after that merger, the combined galaxy may continue existing for trillions of years, while the rest of the universe slowly recedes beyond the cosmic horizon. Future astronomers living in that distant era might look into the sky and see only the stars within their own galaxy. The vast population of distant galaxies that we observe today would no longer be visible. From their perspective, the universe might appear far smaller and quieter than the cosmos we see now. They might even struggle to discover that the universe is expanding at all because the distant evidence would have faded beyond observation. This possibility reminds us that we live in a very fortunate moment in cosmic history. The universe is old enough for galaxies, stars, and life to exist, but it has not yet expanded so much that distant structures have disappeared from view. Our telescopes allow us to observe billions of years of cosmic history across enormous distances, and through those observations we can reconstruct the story of the expanding universe. Yet as the universe continues evolving, the visible portion of the cosmos will gradually shrink relative to the total size of the universe. More and more galaxies will drift beyond the horizon created by accelerating expansion. The observable universe will slowly become a quieter place. This long-term future introduces an interesting perspective on the idea of reaching the end of the universe. Instead of encountering a physical boundary, the universe may simply stretch in such a way that distant regions become permanently unreachable. Traveling toward those regions would become increasingly difficult as space itself expands between them. And so the concept of an edge becomes less about a location and more about the limits created by the expanding fabric of space. The universe may not end at a wall or a border, but instead fade gradually into distances that light itself can no longer cross. Beyond those horizons, galaxies will continue shining and evolving, hidden within regions of the cosmos that remain forever beyond our reach, while the universe itself keeps expanding into the deep and silent future. As scientists study the expansion of the universe and the mysterious influence of dark energy, they also begin exploring another deep question about the cosmos. Not only how the universe expands, but how it might eventually evolve in the far future. The universe has already existed for about 13.8 billion years. Yet compared with the timescales predicted for its long-term evolution, this age represents only an early chapter in an extremely long cosmic story. The behavior of expansion will determine what the universe becomes across trillions and even far greater spans of time. Several possible futures have been proposed by cosmologists, each based on how the expansion of space continues to behave and how dark energy influences the structure of the cosmos. One of the most widely discussed possibilities is known as the Big Freeze, a future in which the universe continues expanding forever, while galaxies slowly drift farther apart. In this scenario, stars gradually exhaust the fuel that allows them to shine. Over billions of years, many stars will burn through their hydrogen and evolve into red giants before collapsing into dense remnants, such as white dwarfs or neutron stars. New stars will continue forming for a time as clouds of gas collapse under gravity, but eventually the supply of star-forming material will become more limited. Over trillions of years, star formation will decline as the available gas becomes locked inside stellar remnants or dispersed across enormous distances. Galaxies will grow quieter as fewer bright young stars appear. The night sky within each galaxy will slowly become dimmer. Meanwhile, the expansion of the universe will continue increasing the distance between galaxies and clusters. Regions of space will become more isolated as cosmic structures drift farther apart. Another possible future is known as the Big Rip, a more dramatic scenario in which the accelerating expansion grows stronger over time. If the influence of dark energy increases rather than remaining constant, it could eventually stretch space so rapidly that even gravitationally bound systems begin to separate. In the far future, galaxies themselves could be pulled apart as the expansion overwhelms the gravity holding them together. Later, even solar systems could become unstable if the expansion becomes strong enough. Eventually, the structure of matter itself could be torn apart as space-time stretches at ever-increasing rates. This scenario remains uncertain because scientists are still studying the exact nature of dark energy and how its influence might evolve across cosmic time. Another theoretical possibility is the Big Crunch, a future in which the expansion of the universe eventually stops and reverses. In such a model, gravity from all the matter in the universe would gradually slow the expansion until the universe reaches a maximum size. After that moment, the cosmos would begin collapsing inward. Galaxies would slowly move closer together as space contracts. Temperatures across the universe would rise as matter becomes compressed into a denser and hotter state. Eventually, the universe could return to conditions similar to those that existed during the earliest stages of cosmic history. However, current observations suggest that accelerating expansion makes this scenario less likely under present models. Each of these possible futures reflects different assumptions about the behavior of dark energy and the total energy content of the universe. Astronomers continue observing distant galaxies and studying cosmic radiation to refine their understanding of these forces. Even with advanced instruments, the long-term fate of the universe remains uncertain. What remains clear is that the universe is not static. It evolves slowly across unimaginable timescales shaped by gravity, expansion, and the mysterious energy embedded in the fabric of space itself. The question of reaching the end of the universe therefore becomes connected to these cosmic futures. If the universe continues expanding forever, the concept of an edge may never appear. Instead, the cosmos may gradually grow larger while galaxies drift farther apart across immense distances. And long after the stars we see today have faded, the universe may continue existing in a quieter and colder state, still expanding slowly across the vast and silent depths of space-time.